Welcome to this video about sound waves. We are going to look at how sound waves are produced, what are some characteristics of sound waves, and what is the Doppler effect. A sound wave is a longitudinal wave. It involves areas of compression with higher density or pressure, and it involves areas of rarefaction with lower density or lower pressure. So what makes sound? Vibrations make sound. Let's think about this in terms of a tuning fork. If a tuning fork is struck, it vibrates, and that's what makes sound. When the tuning fork vibrates to the right a little bit, that forms an area of compression where we have higher molecular density and pressure. When that vibrates back to the left, it gives an area of rarefaction with lower molecular density and pressure, and so on and so forth. That as it vibrates back and forth, it's producing a wave with areas of compressions and rarefactions and compressions and rarefactions. Just as the tuning fork is vibrating with simple harmonic motion, the air molecules are also vibrating back and forth with this same simple harmonic motion. So let's look at some characteristics of sound waves. Why can't I hear some sound waves? Well, actually, two things are really important in being able to hear a sound wave: frequency and intensity. Right now we're just going to look at frequency. And for humans, audible sound waves can be heard between about 20 hertz and 20,000 hertz. Dogs usually can hear waves with frequencies higher than 20,000 hertz. And some people obviously have better hearing than others, but for the most part, this is the range of human hearing. Infrasonic waves are what we call wave frequencies that are less than 20 hertz, and then ultrasonic waves would be those that have frequencies higher than 20,000 hertz, those that we can't hear. Ultrasonic waves actually have quite a few different uses and are used by a lot of organisms besides human beings. Dolphins, whales, bats use echolocation, and that's simply using these ultrasonic waves that they send out. And when those waves hit an object, maybe some prey or a fish or an insect if it's a bat, those waves bounce back off of those. They're reflected off of that, and they can then hunt that way or determine where objects are. Bats know what's around them because of these reflected waves bouncing back. Sonar uses this same principle. It stands for Sound Navigation and Ranging, where ships will send out ultrasonic waves, and then they record the reflections of those waves, and they can determine, they can map a sea floor, they can determine if there are other objects around them, and some of these ultrasonic waves are damaging when they're very, very high powered and can be very harmful to marine life. Ultrasonic waves are very useful in medicine. One use for them is to map soft tissues. This is an ultrasound image of a fetus. And what makes this image possible is that sound waves are partially reflected when they reach a boundary between two materials that have different densities. And then the image that's produced by the waves is clearer and more detailed than could be produced by lower frequency sound waves, because those short wavelengths of the ultrasonic waves are easily reflected off of a small object. In order for an image to actually happen, an ultrasonic image to be seen, the wavelength of the waves must be about the same size or smaller than the object. And just a little reminder, remember the frequency and the wavelength are inversely proportional, so these higher frequencies will have shorter wavelengths. Now, these reflected sound waves are converted to electrical signals, which give us this nice little image. Another characteristic of sound waves, pitch. What is pitch? It's basically how high or low we perceive the sound to be. In other words, it depends on frequency, and when the frequency of a sound wave increases, here we have a higher frequency than here, the pitch rises. So high frequency, high pitch, and low frequency, low pitch. And those are respective instruments that make those high or low pitches. So another characteristic of sound waves would be how fast they travel. How fast do they travel? That all depends on the medium through which they are traveling. And why does it depend on that? Because it depends on how quickly the particle vibrations can transfer their motion. And denser materials will transfer sound waves quicker because the particles are closer together. Also, higher temperatures cause sound to travel faster. So if we know that denser materials are going to cause sound waves to be transferred more quickly, that makes sense that in solids, sound is going to travel the fastest. And you can see that that is generally true. And different materials of solids have different speeds of sound. And liquids are going to be next. Liquids will generally be faster than gases. Air is the medium through which sound tends to travel more slowly. Temperature also matters. You can see that air at 0 degrees Celsius versus air at 100 degrees Celsius affects the speed of sound. Sound will travel faster in the higher temperature. So far, we have been showing waves as traveling in a single direction, but sound waves actually travel away from a vibrating source in all 3 dimensions. In essence, sound waves are spherical, and we're going to assume that all sound waves are exactly spherical unless we state otherwise. And because they're spherical, we have a couple of different ways we can represent them. We can look at them as a cross section, which would be right here. If we take kind of a cross section of this sphere, and we consider the center as being the source, these lines here, these going around in circles, those represent compressions, and the rays here represent the direction of the wave motion. Each of these wave fronts actually corresponds to a crest of the sine curve. This isn't a very good sine curve, but you can see that here's the crest, corresponds to that wave front, and there's a crest, and there's the crest. And each of those crests in turn correspond to a single ray. And here we have wave fronts and rays that are very close to the source, but if we have spherical wave fronts that are a great distance from the source, then they can be approximated with parallel planes known as plane waves. And last, we're going to look at the Doppler effect. You'll notice that if you stand on a street corner and a police goes by with its siren on, the pitch changes as it goes by. You might notice that the pitch is higher as it approaches you, and then as the siren is going away from you, the pitch is lower. Why is this true? Certainly the police car isn't changing its frequency as it drives down the road of its little siren. So the reason this occurs is that there is relative motion between this moving siren and this stationary observer, or this stationary observer. And this relative motion affects the way the wave fronts of the sound waves that are produced by the siren are perceived by the observer. You can see that the wave fronts here reach our observer here more often than if this siren were stationary. Also, the wave fronts are reaching this observer less often than if the siren were stationary. And for this reason, the frequency heard by the observer here is greater than the source frequency, and the frequency heard by the observer here is less than the source frequency. Now remember, frequency determines pitch. So if this observer is perceiving a higher frequency, the wavefronts are actually reaching him at a higher frequency, smaller wavelength will be higher pitch. And for this observer, this low frequency of the wavefronts will cause this observer to hear a lower pitch. So it's important to remember that the Doppler effect occurs whenever there is relative motion between the source of the waves and the observer. So either the source needs to be moving or the observer could be moving, and that gives relative motion between the two. And also, we most often associate the Doppler effect with sound waves, but it is a phenomenon common to all waves, including electromagnetic waves like visible light. And you can look into this idea. An object that is going away from the observer will show long red waves, whereas an object that is approaching an observer will exhibit short blue waves when we're talking about light waves. Here's some advanced ideas for you, conceptual challenge questions, a little more research into ultrasound and how that's used medically, and sound waves used to inspect bridges. How do they do that? Or if you have other questions, please feel free to investigate those, and I look forward to seeing you in class.